I'm Meitar Shechter, a former graduate student at Tel-Aviv University and a current visiting student at the University of Chicago, and I will be presenting our work, NeuralMLS, Geometry-Aware Control Point Deformation. This is a joint work with my collaborators, Rana from the University of Chicago and Metzer from Tel Aviv University, as well as with my supervisors, Giryes and Cohen-Or from Tel Aviv University. Shape manipulation and deformation have many applications, such as character animation or shape editing, just to name a few. Our focus in this work is to provide a simple and intuitive interface for shape manipulation that can be used even by a novice user without any expertise and without limitation on the surface representation. This while still producing realistic results. In the recent years, neural networks have shown promising capabilities and shown to have some certain innate inductive biases, such as a tendency to converge to piecewise smooth solutions, which are particularly suitable for shape deformation of manufactured objects. This motivates our approach, which is to build upon the moving least square framework, which provides a simple interface with introducing learning into the deformation parameters calculation in order to exploit those beneficial biases neural network exhibits. Shape deformation has been extensively studied over the past decades, but current methods suffer from various limitations. Some are limited by the surface representation. For example, in ARAP by Sorkin and Alexa, a connected mesh with good Laplacian approximation is required, and artifacts can appear otherwise. Other limitation can be the required resources, which can render the method inappropriate for certain applications, such as in Keypoint Deformer by Jacob et al., where a dataset of the same shape category needs to be in hand. Other methods might require more expertise in order to be applied efficiently, such as a cage-based deformations method or freeform deformations. Arguably, the simplest method is the one based on control points, where the user simply needs to annotate handles in space, which he can then manipulate. When considering the question of how to construct the weighting function or influence each control point have throughout space, one is usually aimed to gain desired properties for the deformation, which are derived from the weighting function. Such properties includes interpolation of the control point displacement, smoothness of the deformation, and semantic awareness. In this work, we aim to replace the heuristic-based weighting function within the MLS framework with a learned one, in order to keep the simple and convenient interface of the original method, but introduce the desired biases neural network exhibit. So, as our work is built upon moving least squares, I'd like to give a brief overview of the key principles of the method. MLS is a control point-based deformation approach. Once the control point and their displacements are given, MLS constructs for each point in space a weighted least squares objective that we would like to minimize as a function of the deformation. Two things are left to determine in order to solve the minimization problem: the space from which the deformation is taken, and as a closed form solution can be obtained when constraining the deformation to be an affine similarity or a rigid one. Those are usually being used, as well as in our work. And the second one is the weighting functions, where the common one being used is based on the inverse distance. In this work, we focus on the weighting scheme and offer the following perspective. Eventually we need, for each query point in space, to determine the weight each control point have in that point. To do so, we fit a parametric model that outputs each of the control point influence at the desired query point. This is in contrast with current methods that offer explicit interpolation kernels that allow for the evaluation of the influence of each control point at arbitrary location by sampling the kernel. For most cases, we'd like the influence of each control point to resemble a step function throughout space, together with smooth transitions between the region of influence and the region of no influence. This type of weighting function leads to piecewise deformations that avoid discontinuities, where we opt that the region of influence to corresponds to a semantic part of the shape, for example, a wing in an airplane. Therefore, we pose the weight determination problem as a soft classification over the entire space by predicting probabilities for each point in space and partitioning the space into soft regions of influence of each control point. Each point in space should be labeled by one of the control points, corresponding to the idea that this is the control point who should define the deformation that will be applied to this particular point. We therefore train a neural network to solve these classification tasks. We treat each control point we have from the user as a class and train the network to output the corresponding class based on the control point's XYZ position in space. Then, given a new arbitrary point in space as input, the network assigns softmax probabilities to each class, or in other words, to each control point, that are then being used as weights in the MLS framework. Our architecture is a simple multi-layer perceptron, with the last layer dimension being the amount of control points we have in N, and our objective is to minimize a categorical cross-entropy classification loss on the same set of control points, meaning the control points themselves constitute our training data, where we have one data sample per class. Hence, our complete method is as follows. We first have a warm-up phase where we construct and train the network using the given control points. As the number of network parameters and training example is small, this phase takes only several seconds, even on a personal laptop. Once we finish training, we pass our entire shape through the trained neural network in order to gain per point weights. During inference, the user can interactively displace the control points and generate new deformed shapes using the MLS solver. As we train our network in a self-supervised manner on a single input shape, we inject into the deformation parameters awareness to the control point geometric configuration, which is usually tightly related to the underlying shape geometry. This results in each weighting function being dependent on the entire control point configuration rather than just the control point itself. We illustrate this property using a one-dimensional example for clarity. As can be seen on the left, the weight distribution of each control point is different, as it depends on the proximity to its nearby points. While in plain MLS, the weight distribution is identical and only shifted. This is further demonstrated when we displace a single control point. While in MLS, only the weight distribution of the displaced point is affected, in NeuralMLS, also the adjacent control point weight distribution are adjusted. This is because we pose our problem as a space classification one, and each control point also acts as a negative example for all the others during training. Besides the geometry awareness, as we enjoy the inductive biases of neural networks, our method can produce more piecewise smooth deformations. This is again illustrated using a one-dimensional example for better clarity. As the weight distribution of MLS explodes near the control point location, as can be seen on the bottom left, a sharp change in the deformation function is created near those regions, making the deformation less smooth compared to the one produced by our method depicted at the top right, who doesn't suffer from those large peaks in the weighting function, as can be seen at the bottom right. This figure also illustrates the more piecewise nature of our deformation function, visualized in the top of the figure by the linear interpolation in between control points, suggesting each point in space is influenced only by its two adjacent control points and ignoring the rest. This is also visible in the bottom of the figure, as our weight functions are more evenly distributed over each control point adjacent region, compared to plain MLS. As previously mentioned, a good property for a control point-based deformation is to be an interpolation, meaning treating the control point displacement as hard constraints rather than soft ones. While in our method, we relax the interpolation property into an approximation one in order to allow the smoothness bias of neural networks to be introduced, we can control the approximation degree by a simple temperature parameter incorporated in the last softmax layer. Now I'll show some comparisons to existing methods. As can be seen in the insets, our method produced more pleasing results and is less prone to artifacts such as bending the legs of the chair or squishing the plain nose. This also demonstrates some limitations of existing approaches, such as the mesh needs to be connected for ARAP to be applied, or inapplicability of key point deformer due to the need of data from the same shape category. Here I show some quantitative results. We compare the average difference between the mean curvature of the shape before and after the deformation as a mean to quantify the details preservation of the deformation. Our method achieved better results on all four shapes, and I refer the audience to our paper for further details and comparisons. Our deformation method does not come without limitations. As our method is agnostic to the surface representation and quality, it ignores such representation if exists. Such information can improve the deformation quality, and other methods that do utilize such information can produce better, more satisfying results in those cases. To sum up, our method provides a simple and intuitive interface for shape manipulation and deformation, which can be applied on both meshes and point clouds in a surface representation agnostic manner. By building on the MLS framework and replacing the weighting function with a neural network, we can leverage the biases networks have and obtain more piecewise smooth deformations. Thank you for listening. Our code will be released soon, and please check out the paper for more information.